A steady two-dimensional water jet that's 4 centimeters thick and then a meter deep into the board, and has a weight flow rate of 1,960 newtons per second, strikes an angled barrier. Pressure and water velocity are constant everywhere. 30% of the water passes through the slot, and the rest is deflected symmetrically through the other two jets. Calculate the horizontal force needed to hold the barrier in place. There's a lot going on in this problem, but if we look at it logically and put it together, it shouldn't be a problem to solve. First thing I do want to do is I want to draw a free body diagram, which I actually have sketched here already. So I'm going to draw my control volume around it because I need to know what's going on. And so I'm going to draw my control volume here as such. And so what I have is there's my control volume. And I've got it all drawn orthogonally to the jets coming out of the plate. So let's make our assumptions and then get our data together. So I'm going to assume fixed CV because it's not deformable. I'm going to assume one-dimensional inlets and outlets because, once again, I drew it like that. And so I know that they're one-dimensional. I'm going to assume a steady flow. Why do I assume a steady flow? There's nothing in the problem that says it's unsteady. Lastly, I'm dealing with a water jet. Water is generally incompressible. So we're going to assume constant density. Now for this one, there's really a lot in the problem definition. And so we really need to pay attention and write those things out so we can start piecing this problem together. So we've got a steady two-dimensional water jet. And actually, let's give these, I'm going to label the inputs and outputs so I know what's going on. So I've got 1, 2, 3, and 4. 1 is the input, 2, 3, and 4 are the outputs. And so let's just go through and take the write the data down from the problem. The first is I've got a water jet. It doesn't give me a temperature, so we'll just assume 998 kilograms per cubic meter. It's 4 centimeters by 1 centimeter, 4 centimeters by 1 meter coming into it. So then I know the area coming in is going to be 1 meter times 4 centimeters, so 0.04 meter. And that will give me my area that's coming in. And it's got a weight flow rate of 1916 newtons per second. That's coming in. So my weight flow rate at 0.1 is 1,960 newtons per second. Remember, all the weight flow rate is a mass flow rate times gravity. So we get a weight flow rate. Strikes the angled barrier. Pressure and water velocity everywhere are constant. So that means V1 is V2 is V3 is V4. And P1 is P2 is P3 is P4. Pressure part's really important because since the pressures are equal everywhere, we're not really going to be worrying about that force pushing on anything. So 30% of the water passes through the slot and the rest is deflected symmetrically. So if I've got 30% of the water passing through the slot, what that tells me is we look at it and I've got a weight flow rate coming in at 0.1. That which means I have 30% of it at 0.2. Let's write this another way. So I got weight flow rate, and if I multiply that by 30%, that's going to give me the weight flow rate at 2. Now this will also work for the mass flow rates. It's just divided by gravity. The rest is deflected symmetrically. So what does that tell me? Well, if I've got 30% going in at 2, that leaves me 70%, which tells me that 35% of it is going out at 3 and 4. So just from the problem definition, we have a ton of information there that we can calculate. What do we got to find? I want the force in the x direction. What's that horizontal force? One other assumption I am going to make, because we don't have anything in that, we're going to neglect gravity. We're just not going to worry about the weights. And truthfully, it really doesn't matter if we neglect gravity or not, because we're looking for the horizontal component, and that's really not going to come into play with what we're doing, because all the gravity is going to be is going to be in the vertical component. So what do we do? Well, we're going to go and we're going to look at our conservation of mass. Now, the great thing is the velocity is the same everywhere. And so I can calculate that out I can do it at point 1, 2, 3, or 4. I have all the information at point 1, so I'm going to calculate it out at 1 and then just know it applies everywhere. So the velocity of 1, what's going to be? Well, what is the mass flow rate? Is rho VA, so the weight flow rate is rho VA times G. So I'm just going to take my weight flow rate at 1. I'm going to divide it by gravity to give me my mass flow rate, and then I'm going to divide it by density times the area, and that's what's going to leave my velocity. So now at this point I just plug the numbers in. 1960 newtons per second. We're going to divide that by gravity. We're in the metric system, so 9.81 meters per second squared. I'm going to multiply that by the density of water, 998 kilograms per cubic meter. And then I have my area, 1 meter times 0.04 meter. Now let's look at the units. So velocity, I'm expecting length per time. So I have a newton. What is a newton? Remember, F equals ma, so 1 newton is 1 unit of mass, which is a kilogram, accelerated by 1 unit of acceleration, meters per second squared. So we're going to replace the newton with that. We got a kilogram there, second squared there, second squared there. Still leaves me 1 second, so I've got meters per second on the top. If I look at the bottom, 1 meter, 2 meter, cubic meter divides out cubic meter, so I'm left with meters per second, which is what I expect. Tells me the velocity at 1 is 5 meters per second. Because of the problem statement, that's also the velocity at 2, 3, and 4. So V2, V3, V4. So I know that all of my velocities are 5 meters per second. Now, for my conservation of linear momentum equation, I'm going to need mass flow rates. So let's calculate that out. So my mass flow rate at 1 will be easy because I have my weight flow rate divided by gravity. So 1960 newtons per second divided by 9.81 meters per second squared. Now I calculate that out. You should be getting 200 kilograms per second. Now I don't know the areas at the other places, but I do know how much mass is going through each one. So to find 2, as we said before, well, that's 30%. So I'm going to take m.1, multiply it by 30%. And so when I do that, I'm going to do 200 kilograms times 30%. That's going to give me 60 kilograms per second. m.3 is going to be equal to m.4 from the problem definition that tells me that it's m.1 times 35%. So in those other two directions, we have 70 kilograms per second going through the upper part and the lower part. So now we have our velocities, we have our mass flow rates, we can go to our conservation of momentum equation. So conservation of linear momentum, we're only worried about the x direction. So this is our x direction momentum equation. And so we'll sit there and we'll write that out. It's the sum of all the forces in the x direction, the body and surface forces. We have no body forces because we're not worrying about weight, weight, nuclear, or electromagnetic. We only have surface force, and because the pressure's all the same everywhere, we're not really worrying about any of that. All we have is the force pushing against it. And that force is drawn in the negative direction because we're just going to take our typical up and to the right as positive. So I have negative F. What does negative F equal to? Negative F is equal to the sum of all of the mass flow rates times the velocities, so our momentums, the sum of all the momentums coming out minus all the momentums coming in. So let's look at that. Mass flow rate at 2 times the x velocity at 2, that's coming out, plus the mass flow rate at 3 times the x velocity at 3, plus the mass flow rate at 4 times the x velocity at 4. So remember, this is 1, 2, 3, and 4. And now that's minus all the momentum coming in, which is minus m.1 u1. Now, all we have to do is start plugging in numbers. So negative F. Negative F is going to be equal, well, mass flow rate at 2 is 60 kilograms per second times U2. Well, that's 5 meters per second. And it's all in the x direction, it's all positive x. Mass flow rate at 3 and the mass flow rate at 4 are going to be the same thing, so 70 kilograms per second. The x velocity from point 3 is not 5 meters per second because there's an x and y component of that. Also, they're operating in the negative direction, so you're looking at negative 5 meters per second times the cosine of 55 degrees, because we need that projection. We need that x direction. So if I do that at 4, I'm going to get the same thing. It's going to be m dot 4, which is 70 kilograms a second, times a negative 5 meters per second, times a cosine of 55. So I'm just going to take that part, multiply it by 2, because it's the exact same equation. That's everything coming out of the system. Now we have to do everything coming into the system. So we're minus 200 kilograms per second, because that's the mass flow rate coming into the system, times the velocity coming in the system, 5 meters per second. It's all in the positive x direction, so there's nothing that we have to do with that. So now if I go and I calculate this stuff out, what am I going to get? Well, I'm going to get negative F is equal to negative 1100 newtons. Multiply through by 1. So the force to hold this guy is going to be 1100 newtons, and it is a positive number, so that means that we picked the correct direction. And that's all there is to it. This problem seems really complex, but if you slow down, write down everything that you know, and just start piecing away at it, it's not too bad.